Have you ever stopped to wonder how our digital world just keeps getting faster and more reliable? You know, a lot of the time, the most powerful solutions are actually the most elegant. Today, we're going to pull back the curtain on one of networking's most ingenious little tricks, EtherChannel. It's this amazing technology that takes what should be a network weakness and turns it into a massive strength. So, let's unravel this networking paradox and see the clever solution that keeps our connections blazing fast and super strong.
I mean, it seems perfectly logical, doesn't it? If you want a faster, more resilient connection between two network switches, what do? You just add more cables. It's the most intuitive solution you could possibly think of. Double the cables, you should get double the speed. And hey, you've got a backup if one of them fails. Simple.
But here's where things get really weird. When you actually do that, your network's own safety systems kick in and disable those extra connections. It's this super frustrating paradox where the very thing you're doing to make your network stronger actually makes it weaker. So today, we're going to find out exactly why that happens and how a brilliant piece of engineering solves this problem for good. So here's our game plan. We'll start with the core problem, what's often called the redundancy paradox. Then we'll explore EtherChannel's fantastic solution of creating one logical superhighway. After that, we'll look at how these links are actually formed, dive into the fascinating science of how traffic gets balanced across them, and finally, we'll see why this technology is still a cornerstone of modern networking.
Okay, let's jump in. Section 1, the redundancy paradox. This is where we get to the root of the problem, and it all starts with a protocol that's designed to protect the network from, well, basically destroying itself.
And that protocol is the spanning tree protocol, or STP for short. Its one and only job is to prevent something called a layer 2 loop. Trust me, you don't want one of these. It's a catastrophic situation where data packets just circle endlessly, and it can bring an entire network to a grinding halt in seconds. To do its job, STP enforces one simple rule. There can only ever be one active path between any 2 points, period.
And this is exactly where the conflict happens. You go and plug in those extra cables, hoping for more speed and reliability. But STP sees those multiple paths, and, doing its job, it thinks, whoa, danger, a potential loop. So, to keep the network safe, it puts all but one of your expensive connections into a blocking state. They're plugged in, but they can't pass any traffic. So what's the result? A ton of wasted hardware and idle bandwidth just sitting there doing nothing.
So how in the world do we get around this? We can't just turn off the network's most important safety feature. Well, the answer isn't to fight the protocol, but to outsmart it. The solution is all about changing what the protocol sees, and it is just remarkably elegant. And here it is, EtherChannel. It's a technology that bundles a group of physical wires and then presents them to the rest of the network as one single logical connection. The best way to think about it is like taking 4 separate country roads and seamlessly merging them into one massive 4-lane superhighway. This is where you see the absolute genius of EtherChannel. It pulls off this kind of architectural sleight of hand. It doesn't fight spanning tree, it just tricks it. By grouping those physical cables into one virtual port channel, STP doesn't see a bunch of dangerous paths anymore. Nope, it just sees one big, safe, logical link. And since there's no loop to worry about, it keeps the entire bundle active. Just like that, all your cables are forwarding traffic, exactly like you wanted in the first place. This one simple trick delivers 3 huge wins. First, you get aggregated bandwidth. 4 1-gigabit links literally become a single logical 4-gigabit link. Second, you get incredible redundancy. If one of those physical cables in the bundle fails, traffic instantly and seamlessly shifts to the others. And STP doesn't even flinch. The network just stays up. And third, it makes your life easier. You configure and monitor one logical link, not 4 or 8 or even more physical ones.
Okay, but how is this logical superhighway actually built? It doesn't just happen automatically. There are really 2 main ways to form an EtherChannel, and the choice you make is a classic case of risky manual control versus automated safety.
On one side, you've got the static on mode. This is the brute force approach. You just tell the switch, make these links a channel, now. The danger here is that it does absolutely no safety checking. If you've misconfigured something on the other end, even something small, you can create some serious network problems. But then, on the other side, you have dynamic protocols. This is the intelligent, safe method. The switches actually have a conversation. They verify that all the settings match up before they agree to form the bundle. And this morning gets right to the heart of why this is so risky. Without that automated safety check, you could literally be sending your network's precious data into a traffic black hole. A link with a device on the other side isn't even part of the channel. The data just arrives and disappears. That's exactly why dynamic protocols are almost always the recommended best practice.
So when we talk about those dynamic protocols, there are really two main players. PAgP, which is Cisco's original proprietary protocol, and then there's LACP, which is the open industry standard. In today's world of multi-vendor networks, LACP is the undisputed champion. It works with equipment from pretty much any manufacturer, and it has more advanced features like being able to designate hot standby links that are just waiting to take over instantly if an active link fails.
All right, so our links are bundled and they're all active. Awesome. But how does the switch decide which data packet goes down which physical wire? This is easily one of the most misunderstood parts of how EtherChannel works. The common myth, the thing everyone thinks, is that it works like a dealer handing out cards. One packet for link 1, the next for link 2, and so on, in a simple round-robin style. Now, this sounds fair, but it would actually be a complete disaster for network traffic because it could cause packets from a single conversation to arrive all out of order. The reality is way more sophisticated. EtherChannel uses a mathematical process called a deterministic hashing algorithm, and its main goal is to make absolutely sure that all the packets belonging to one single conversation, like your video call, always travel down the exact same physical path. This is what preserves the original order and keeps everything working smoothly. Here's how it works in a nutshell. The switch takes a quick peek at the information in the packet header, like the source and destination IP addresses. It feeds those values into its hash function, which then spits out a number. That number corresponds to one of the physical links in the bundle. And here's the key. Since a single conversation will always have the same IP addresses, it will always get the same hash result, and so it will always use the same physical link. It's totally predictable by design. Now, the cool part is the network engineer gets to choose which of these values to feed into the hash. Should it be based on MAC addresses, IP addresses, or if you want the most variety, you can use the TCP or UDP port numbers. The goal here is to pick the values that have the most randomness or entropy in your network's traffic. If you choose well, the load spreads out nice and evenly, but a poor choice can lead to one link getting totally overwhelmed while the others are just sitting around nearly empty. And hey, here's a pro tip that makes a huge difference. Always try to use a number of links that's a power of 2. So 2 links, 4 links, or 8 links. This perfectly lines up with the binary math that's going on behind the scenes in the hashing algorithm. This one simple design choice is really the key to ensuring you get the most even and predictable traffic distribution across all your physical wires. Okay, so last section. You might be thinking a technology this old is probably history, but EtherChannel isn't just relevant today. It's actually more important than ever. It really is a bedrock of modern, resilient networks. I mean, EtherChannel is the workhorse of the modern campus network, forming those high-speed backbones between all the switches. It gives us powerful, fault-tolerant connections to our most critical servers. But its evolution is what's really amazing. With technologies like multi-chassis EtherChannel, you can now build a single bundle with links that physically connect to 2 completely separate switches. That gives you the ultimate in device-level redundancy. If an entire switch fails, your connection stays up. It's incredible. And that really brings us to the core takeaway. This isn't just some obscure feature you might use once in a while. It's a fundamental building block of network design. It gives us an elegant solution that delivers scalable bandwidth, high availability, and simplified management, all in one neat package. You know, EtherChannel reminds us that sometimes the most powerful engineering is based on a really simple, clever idea, a trick that just changes the rules of the game. It makes you wonder, doesn't it, what other simple tricks are out there, quietly forming the invisible backbone of our incredibly complex digital world?